Please join me in welcoming Dr. Zaiane to our workshop.
Well, thank you for the introduction. I am very pleased to be here and actually honored to be at the University of Manitoba, 1877. This is one old university, older than U of A, where I'm working. I'd like to thank Marcia Friesen and Bob MacLeod for this invitation and this opportunity. The talk is titled The Potentials and Pitfalls of Big Data. I didn't actually choose that title. That title was suggested by Bob and Marcia, and I said, well, that's perfect. That's actually, it fits what I may want to convey. But I will not divide it into potentials and then the pitfalls. The plus and minuses will be throughout the talk. Okay, it's not working anymore. Big data, that's the topic that we'll address today. We hear it everywhere. I mean, if you're here, it's because you heard already the term, and you probably have started using it, and many people are using it. It's becoming almost a common term, so common that actually you will find even jokes in newspapers and even cartoons about big data. That shows you how common the term is used. Unfortunately, it's a misnomer. I personally don't like it, but I have to use it because everybody's using it. I'll tell you why I don't like it and why I think it's a misnomer, because people focus on big. Yeah, big is important. It's a big part of it, but it's not the only thing that makes big data what it is. So I prefer calling it rich data, but it's not as sexy as big data, and that's why people continue to use big data. So let's call it big rich data. Okay, this remote doesn't work anymore. Maybe the batteries are dying. It's fine. It's okay. It's okay. So let's see what people say about big data. Well, apparently the claim is that big data holds the potential to yield new insights to help optimize business process and assist in making better decisions for organizations to gain business advantage. Wow, this is amazing. This is a dream. That's why I put it in a cloud. Huge potential. But wait a minute. Isn't it what we said about data mining for years? That's exactly the same thing. I mean, I've been working on data mining since the early 90s, and that's exactly the claim. So what's about big data? If you look at the trend, so this is from Google Trends. Google Trends tell you how often people submit queries with certain terms. And you look at data mining since 2005, approximately. This is data mining is in red, and you can see that the trend is going down, so it's less popular. Big data was absent, and then suddenly is skyrocketing, starting in 2012. It existed before that. This has to do with the fact that there's now a stigma attached to data mining, the term data mining, and many people in the industry don't actually use data mining anymore, even though now it's coming back. They started using terms like business analytics or business intelligence. So if I look at the trend for business intelligence, that's in yellow, and you can see that it's fairly consistent throughout the years, and it's catching up with data mining. Another term that is now, well, it's been around for a long time, but it's very attached to the concept of big data is machine learning. Machine learning, you can see that it wasn't that popular, but it's going up again with the rise of big data. Okay, with the rise of big data, people are hearing about machine learning and they're interested in machine learning. Another synonym to big data is data science. So it's not big data per se, it's big data analytics. So a synonym for big data analytics is data science. Even though that term existed before in statistics, even in the 60s, they were using data science for statistics. So if I put data science there, you can see, like machine learning, is going up with big data. So there's a kind of a hype there. There's a lot of hype because of that huge rise. The slope is quite high. If I think about another term that is seeing a huge gain in popularity besides big data, there's quantum computing. Who has heard of quantum computing? Yeah. Quantum mechanics has been around for a while, but now quantum computing is becoming very popular, and there's a lot of investment also in quantum computing by big companies and also by government. So if I compare them, you can see that they're not comparable. Actually, quantum computing is still dwindling down. It doesn't have the same momentum as big data. So what's going on? What's going on with big data? There's this magic. So it's not big data, there's a big magic. It's so magical that now everybody's claiming to do big data. And as I said, it's even in cartoons. So he's one of them. A coach telling his team, remember, the other team is counting on big data insights based on previous games, so kick the ball with the other foot. Who has heard of the AI winter? The winter of AI. Interesting. Very few. Okay. For those in the AI research who have played with AI anyways, probably know of what happened in the history of AI, artificial intelligence. Very quickly, I'll give you the history of AI. So basically, it started after the Second World War. A very famous person called Alan Turing, who participated in deciphering the code of the Germans, he's a British, wrote a very interesting book. The book titled Computing, Machinery, and Intelligence. And he talks about how computers, these new machines that we barely used to calculate trajectories of missiles and stuff like that during the war, now we will use them for the common good. Well, they will become eventually intelligent. And in his book, he actually talked about the Turing test, where we will be able to test whether a machine is more intelligent than a human or not. At what point will it be more intelligent than a human? So we consider him not only the father of computing science, but he's the father of AI. In 1955, John McCarthy and other colleagues wrote a proposal to run a conference, and a conference on intelligent machines. And in that proposal, he suggested the term artificial intelligence, that he coined the term artificial intelligence. And the proposal was accepted. The conference was organized at Dartmouth in 1956. And for some weeks, people were debating about how to make these machines intelligent. And that was the beginning of the field of artificial intelligence. So their hypothesis, their thesis is that the human thought, the human activities, the human intelligence can be broken down into parts that can be coded into machines. And then you can build an intelligent machine. People believed in this theory, and a lot of money was flowing into artificial intelligence research. Governments in the US, remember that was the Cold War, so we didn't want the enemy to have that before us. So there's a lot of investment there. Same thing in Europe. So, and there were many interesting, successful stories. That's when neural networks were also were seeing the first success. So there was a lot of belief in this hypothesis. Until 1972, Hubert Dreyfus from Berkeley, a philosopher, wrote a book about what machines cannot do. And actually, he basically said this artificial intelligence is utopia. We can't get the intelligence of a human inside a machine. And then Congress decided, okay, now all this funding going to AI, we have to shift it to other fields that need the funding. And basically, AI went to disrepute. People were not interested in AI, except some believers who continued to work. And that continued till the 80s when the Japanese, I don't know if you remember, the Japanese announced the 5th generation project where they were going to use Lisp and Prolog. These are two languages that were devised for artificial intelligence. They were building these machines where these languages are hard-coded. And then suddenly the Americans, as well as the Europeans, said, ooh, we don't want the Japanese to be there before us. They certainly know something we don't know. So they started putting money again in artificial intelligence. And then you see another big slope going up. At the same time, there was also the success of expert systems in the 80s. Expert systems, the market of expert systems reached a few $1 billion in medicine, manufacturing, and chemistry. So there were many expert systems built that were very successful. So people said, and expert system is part of AI. So people started believing again until the collapse of the Lisp machine market. They realized they can't sell this. So again, disrepute. Okay? And it's because of some believers, and thanks to the fact that machines became faster, bigger memory, and so forth, and because AI was split into pieces, there are different subfields in AI, and people were focusing in subfields, that's how AI continued. So this is what we call the winters. The winters of AI are these dips, these valleys, okay, where basically the funding dried out. The governments were not funding AI anymore. The interesting thing now, it looks like it's on a plateau, but in my belief, we will see a third winter, and I'll tell you why. If you look at a company like Google went on a shopping spree last year and this year, and they acquired many startups specializing in AI and machine learning. And Larry Page recently in an interview said, Google is not just a search company, we are an AI company. So many are investing in AI yet again because we think we are getting very close with the fast machines to reach what we call the singularity. I don't know if you heard of the technological singularity. But again, you have people like Hawkins, who a week ago wrote an article saying that AI would lead to the end of the human race. I mean, you have these battles between two schools, the believers and those, the skeptical, who said no, okay, it's utopia, or dangerous. It's not utopia anymore, but it's dangerous. So this is not specific to AI. All technologies follow what we call the Gartner hype cycle. So you have believers in the beginning, some interesting success stories, and then you have funding, believers, until it reaches a certain point where people kind of become disillusioned and say, no, this is not working because of some failures, or because the expectations were too optimistic and they were impatient, and then it goes down. And because you have some believers who continue, then it goes back up until it reaches a plateau. So all technologies follow this trend, plus or minus. So is it something that will happen to what we call big data? We don't know what it is yet. I'll talk about it. So will we see a winter of big data? Will we fall in this disrepute like AI? By the way, this is not Winnipeg because it's not flat. There's a hill. So what is big data? Well, you ask different people, they will give you different answers based on what magazine they read, what article in the newspaper they read. So that's the opinion of the journalist who wrote it. I like using this metaphor. So this is a story out of India, folklore, but you find it in China and other Asian countries. The story says, well, they put some blind people in a room with an elephant, and they asked these blind people to describe what's in there. So each one touches part of the elephant, and one says, well, it's a rope holding the tail. Oh, it's a snake, or it's a carpet, or it's a wall, or it's a tree. They don't see the big picture. That's exactly what is happening with big data. Okay. So what is the current reality of big data? There is a famous psychologist and behavioral economist from Duke University. His name is Dan Ariely. And last year in his Facebook wall, he wrote a very interesting observation. He said, well, big data is like teenage sex. What? Well, everybody talks about it. Nobody really knows how to do it. Everyone thinks everyone else is doing it, so everyone claims they're doing it. And it's so true. And people are focusing on the technology of big data, and they're often missing the point. So big data, the technology itself is secondary. It's important, but it's secondary. What is important is what can we do with that? Okay. And actually, I can even go further. We don't need big data. What we need is big information, the information that we can get out of this data. Because the data itself, well, who cares? We have actually, we had large and big, complex, rich data for a long time. So if you look at the industry today, this is from Forbes. About last year, they say that the market value of big data reached $16 billion, which is phenomenal, it's huge. And they estimate that it will top the $50 billion by 2017. And they give some partitioning in the industries, who's spending what and for what reason. It's actually quite interesting. And what is even more interesting, why is this happening? So another report that came actually a few weeks ago, this is a report by Accenture and General Electric. They surveyed their customers, and they published this report. They say it's for 2015, but it came out, I think, in October, or is it November? Oh, October 2014, so at the end of October. And they said that 87% of enterprises believe big data analytics will redefine the competitive landscape of their industry within the next 3 years. So it's very, very, very important. But more than that, 89% believe that companies that do not adopt big data analytics in the next year risk losing market share and momentum. So it's not a question of it's important, but it's actually, there's a threat if you don't go there. You have to jump on that train. If you miss the train, you're doomed. And that's 89% of the companies asked by Accenture and GE. More statistics. They were asked what proportion of their IT investment goes to big data. And you can see that almost 1/5, so 22%, are spending more than 30% of their budget on big data. Half of the companies are spending between 20 and 30%. That's phenomenal. And then when they asked, will that go up or down next year? The majority are saying it's going up. 75% are saying it's going up. So the trend is going up. More statistics from the same report. So they divided it into different groups of their customers. And they all agree, and they said, how important big data analytics relative to other priorities in your company? And in orange, these are the people who are saying that's the top priority. And you can see it's extremely important for most businesses. And whether it's in not the top, but among the 3 top, that's in the green. Only very few have 3% saying, oh, it's not that important. So definitely we have to look into that. And other questions in the same survey, these are very interesting surveys, that's why, questions, that's why I'm sharing them here. They ask the question, if you are unable to implement big data strategies in the next 1 or 3 years, what are the fears? So again, this is a question of fear, not a question of it's useful. I have to do it because my competitor is doing it. So the fear, number one, and again, orange is the top, and among the 3 top, it's the green one. And you can see that 28% are saying our competitors will gain market share at our expense. So I don't know what it is, but I have to do it. Otherwise, I'll die. That's the fear. So where does all this come from? Short history. It's not that long ago. Actually, people are trying to go back in 1940-something in the history of big data. I don't buy it that way. My history for big data starts in 2008. So 2008, there was an article in the Wired magazine where they used big data for the first time as a rhetorical term. The article was called Petabyte Age. So basically they were talking about what we considered big in the past and what is big today. And when I was doing my PhD in the 90s, megabytes was huge. We didn't have actually disks to hold that. Now megabytes is nothing. We're talking about not even gigabytes, we talk petabytes and beyond. In that article, they just talk about the size as being a moving target, what we consider large or big. It's very relative. So an answer to that article was a white paper published and written by 3 eminent professors from Berkeley, University of Washington, and CMU. And they try to define what big data is. And basically, roughly speaking, and this is from the article, they said big data typically means applying tools such as machine learning, and I highlighted machine learning, to vast data beyond that captured in standard databases. And this is very important, standard databases. And also vast data. So the size is important, but there's also the complexity of the data is in that kind of definition. It's a vague definition. But they give examples of what cannot be captured in standard databases. They mentioned web browsing trails. So this is behavior of a user on the web, social media, sensor data, surveillance data, and so forth. So basically, big data refers to massive amounts of data, but complex data that are difficult to manipulate and understand with today's traditional processing means or methods. Okay, so we need to find something else to do it. Now the problem comes from an article, the problem, I think it is a problem, comes from an article in Nature that same year, 2008. So Nature had a special issue on big data. And what you see here is the online version of the editorial for the special issue. And if you look carefully, so that's in September 2008. If you look carefully, I did a search. That circle there, that's a search within my browser, searching for big data. Big data appears only once in the editorial. And they don't say big data, they talk about big data sets. Okay. And they have that picture, big data. That's all. But in the special issue, they have many articles talking about big data, and their title, they have big data, blah, 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 big data, something, something. Unfortunately, all those articles, when you scan through them, they only focus on the size, big data. And I think that's where the misnomer comes from. So what changed things is the team from IBM, the marketing team, not the technical team, but the marketing team, they came up with this nice, fancy idea to present dimensions of big data as V's, the 3 V's, the big 3 V's. There were 3 in the beginning. I'm showing 4 here. The fourth was added later. So the three V's are volume, because we have a lot of data. Apparently in the recent report, they calculated that 90% of digital data today was created 2 years ago, in the last 2 years. Not 2 years ago, but the last 2 years. So everything else is representing only 10%. And this is going at an exponential rate. So it's really big. It's getting bigger and bigger. Volume is an important one. So that's V. The other one is velocity. V. Velocity, because this data is coming at us very rapidly. We barely have the time to look at the data, and you have new data coming in. So it's not just the speed of the data coming at us, but it's also the speed of change. The data changes rapidly. What does that mean? So in traditional databases, I'm talking about relational databases, you have a table, you have rows, and you have attributes. Before you build your database, you have to define what we call a schema. Schema are all these attributes in each row, and what is the type of that attribute, and so forth. But when the data changes, it means you have now new attributes. You have to stop that database and rebuild it. And you can't do it when you have data changing all the time. And that's why relational databases cannot handle big data, because of that huge change of the data itself. So the velocity is not just the data coming at you fast. It's not only the change that is fast. There's also the need to access the actionable knowledge from that data has to be fast too, because the competitor will do it before me. And if they do it before me, might as well not doing it, because I don't have any advantage anymore. Okay. So it has to be fast. So you have velocity at all these three levels. Then you have another V, variety. And variety comes from the fact that now the data is not in just one silo. You have many silos. You have many sources. So the variety of sources, but also the variety of the types of these sources. You're not just dealing with some structured data here. There it could be text, it can be tweets from here, it can be images from there. So you have the types of the data sources different, and so the data types. So I just hinted to the images, videos, text, and so forth. So that's another V. The last V that was added later is called veracity. And veracity has to do with the fact that, well, data that you're using and coming from different sources, sometimes it's not even your data coming from outside, has a lot of uncertainty in it. So if it has these uncertainties, how do you ascertain the truthfulness, the veracity of the output that you will get out of the analysis? So you have to be very careful how to eliminate noise, for example, from the data, and contradictions, especially when you have data coming from different sources, you may have contradictions. So you have to eliminate them, otherwise they'll impact your results at the end, and then if you're taking actions on this and it's wrong, then it's dangerous. There's something else missing here in the picture, is that for veracity, and to assess whether what you get is actually not just true, but actually to be able to interpret what you get, you need metadata. You need data about the data. And that metadata, as I'll mention it later, metadata has to be captured from the source in the beginning. So I'll give you some examples. And this is not just true for big data. It has always been true, but it's even more important today. What is that? Well, that's a statistician. It's a statistician coming from another planet. And he's going around the Earth and observing humans. Then he goes back, or it goes back, to its planet and writes a report to the decision makers there on that planet, whether they will invade the Earth or whatever. I don't know what's their decision. But the report says, the average human has one breast and one testicle. Well, statistically it's correct. It is right. It's missing a very important point though. Humans, we have females and we have males. Maybe they don't have it on that planet. And that's the metadata. So without the right metadata, you can't interpret it properly. And that's known in statistics. You think it's just a joke. I made it up. I built this slide and I made up this joke. But it's so true. Look at this one. This is from a newspaper. It says statistics show that teen pregnancy drops off significantly after age 25. I don't know how the editor missed this. But this is real. Is that right? Is that wrong? Well, metadata again is missing. 25 teens? Come on. So this shows the importance of metadata in order to interpret results. Now here we take it for granted. It's common sense that teens are not 25. So a quote that I love here is, data doesn't create meaning, we do. And this has been true for a long time, and there are many sayings about statistics, how statistics can manipulate truth. So here are some quotes. I'll turn to be able to read them because my screen is too small. Statistics can be made to prove anything, even the truth. There are two kinds of statistics, the kind you look up and the kind you make up. Torture numbers and they'll confess to anything. 98% of all statistics are made up, even that one, by the way. Facts are stubborn things, but statistics are more pliable. And the best of all, statistics are like bikinis. What they reveal is suggestive, but what they conceal is vital. So this is also true in big data. So it's actually even more true with big data, and we have to be extremely careful how to interpret what we get out of that. So one other example I want to show, which is typical in statistics. So who knows about the Anscombe quartet in statistics? Oh. So the Anscombe quartet, this is done by Francis Anscombe. It's a statistician. He's still alive. I think he's at Yale. In 1973, to show the importance of considering outliers and the impact of outliers on data, he created 4 data sets. The interesting thing about these data sets is that, and I just printed them there, I took them from Wikipedia, they have the same simple statistical properties. For example, they have the same linear regression line. And if you take the x variable on these 4 data sets, they have exactly the same mean, 9. And on the y, they have the same mean with 2 digits, 7.50. On same variance for x, same variance for y with 2 digits. And even the same correlation between x and y on the 4 data sets. However, when you visualize them, they're completely different. So actually, I'm using this not as, an illustration to show how important it is to consider the outliers and the impact of the outliers. And you can see in the third one, for example, the linear regression was different, but it tilted upward because of that outlier. So the outliers have an impact indeed. But I wanted to use them as an example to illustrate the importance of data visualization. If we don't see it, we can't see the difference between the data sets because they have the same properties. And so I can't emphasize even more, visualization, data visualization is capital, also in big data. At the end, when you find some patterns, you find some knowledge or whatever, you want to present it to the decision makers, it has to do in a format that is not just pleasing, but also I can make sense out of it. And unfortunately, it's not just us, the computer scientists. I work on data visualization, but I don't think I have the right skills to do the data visualization. We need people in communications, people that have artistic skills and so forth to help us out. Here's an example of data visualization that I like, but it illustrates some of the concepts that I often want to convey about data visualization. A good visualization is a visualization that allows you to render more than just 2 dimensions on a two-dimensional medium, which is the paper or the screen. So in this particular case, this is a visualization from a Kappa software company. They're talking about big data and how it is distributed in the different industries. And you can see here I have many different dimensions. There's a dimension about structured or unstructured. There's a dimension about variety, volume, and velocity. There's the color, meaning if it's an internal or external. So at the same time, they represent many, many different dimensions. So you can see many things at the same time. Okay. So can big data improve analytics? Today, most of the effort done in data science and big data is towards predicting consumer behavior. So all these big companies that are trying to sell you something, they are using today big data to better understand what you want and what you may want in the future. You'd be surprised, even better than yourselves. And I have many examples, but I'm not showing them all here. Doesn't always work. Second cartoon. Two colleagues talking to another one saying, Twitter and Facebook can't predict the election. This has happened after there were discussions about elections being predicted with Twitter. But they didn't predict, but they did predict what you're going to have for lunch, a tuna salad sandwich. Oh, you're having the wrong sandwich. I still believe that they're right. So, again, can big data improve analytics? I remind you what that white paper was saying. Big data typically means applying tools such as machine learning, again I highlighted machine learning and explaining what it is, to vast data beyond that captured in standard databases, such as web browsing, trails, social media, and so forth. So typically, big data is a mix of structured data, semi-structured data, and unstructured data. And typically, this data will not will not fit in the traditional relational databases. We can't scale very well, particularly if we want to distribute them in different places. In addition, if we have a rapid change of the schema and so forth, indexing it and so forth. So typically, they break the limits of the indexing by row, and that's why we have what we call today NoSQL. NoSQL means not only SQL databases, and these are another paradigm for storing data with key value pairs, such as Hadoop database and Bigtable for Google and so forth. And typically they require very intensive processing that goes and sophisticated algorithms that go beyond what we have today. And what is synonymous with that today, actually is almost synonymous with big data, is the MapReduce type of operations. Who has heard of Hadoop? Okay, many. Hadoop is almost synonymous with big data today. But I warn you, not everything is MapReducible. There are things that are MapReducible. Apparently 80% of the work done at Google is done with MapReduce. MapReduce existed before. In the 60s, in functional programming, the concept was created, except Google used it to calculate the frequencies of terms on all these pages, and then they build the MapReduce framework, and then open source, Apache open source initiative built the Hadoop that everybody is using today. But there are many things at Google that they can't do with MapReduce. For example, there was a paper recently in NIPS talking about how Google detects the emails that are important and the emails that are not important, even though this is a huge problem with the thousands or millions of people accessing their email and getting emails every day. They didn't use MapReduce. MapReduce could not be used. They used Bigtables. So in summary, there are no standard recipes and no standard architectures that can fit in here, hence the need for data scientists. So data scientists, to be able to understand all the jargon here, this is an example for Hadoop and all the other tools that Apache also provides, like Hive, HBase, Mahout. Mahout is a machine learning on top of Hadoop. You have the Hadoop distributed file system and so forth. The Zookeeper. This actually became even more complex because even data scientists now can't follow. You have a complete ecosystem around Hadoop. And you think this is complex. The real landscape of big data today is it's changing every day. You have new companies, new architectures, new solutions proposed. And we need data mining on this to understand what's going on. I mean, I'm supposed to be a specialist and I'm lost. Okay. So I mentioned machine learning many times, just on one slide, what is machine learning? So basically, machine learning is about allowing machines to learn some model out of the data in order to build predictive modeling, to create some prediction, classifying objects. So typically what you have some data that is provided to the machine, and that data is labeled, and then you have other data that is not labeled. And machine learning will go through this as a training process, will go through this and build a model. That model can be a hyperplane separating the groups in the space, or can be a decision tree, can be a set of rules, can be some weights on perceptrons for a neural network, can be many different things. Okay, there are many models, many paradigms to do that. Let's put a happy face on it. It's just a cloud. And then we will use that model for the other objects that haven't been labeled to predict what their labels are. That's what machine learning is all about. So how can we learn from observations in the data to predict something that hasn't been observed or has been observed partially? There are some class labels to add. Okay, so this has been done for many years. And typically, it's done on numbers and some categorical values as well. It can be very large. Okay, so people have been working on scaling up those techniques. But it's not just the fact that it's large. Remember, it's coming at a high speed. So it's a fire hose of data. So people are starting actually thinking about how I can change my model, my learned model, because there's a drift in the concepts. How can what I learned here adapt to the new data that is coming at me, because it's changing all the time. But in addition to the fact that it's coming at me at a high speed, there's this variety. Okay? The data is coming from different places. Some I have control, some I don't have control because they're coming from outside. And they're complex, they're unstructured. In addition to that, they have different types. And I'll get to that. So here I take advantage to add two other V's. These are not in the IBM marketing strategy, but I added the value and I added vulnerability. So value comes from the integration of different data sets. And that's the essence of big data. That's my view of big data. Vulnerability has to do with the fact that by combining different sources, you will discover things that are not in the first source and not in the second source. And when you think that the first source is anonymous and it's not jeopardizing my privacy, neither is the second one. By putting them together, sometimes I may actually discover some private information that I didn't know wasn't concealed properly. So that's the vulnerability. It's not the vulnerability of the data, it's the vulnerability of the people. And I'll show you one example. It'll scare you maybe. So anyways, we are bombarded with stories about how much data there is, and size is not everything. There's also the fact that we have speed and variety, but also the different types. So we have images, we should take advantage of that. We have videos, we also should take advantage of that. We have sound, and certainly we have a lot of text. And there are many applications now trying to take advantage of the tweets, the Facebook, the fora, and so forth. There's a lot of gems hiding in there. And something that we often forget in the data that has and tremendous power, it's the connections that are in the data. Data points are not independent. They're related with some relationships. Of course, you can think of social media. People are connected by friendship, by whatever. But there are other connections. If you take biology, I take, I don't know, the protein-protein interaction, there's a relationship between proteins. And that relationship may depend upon the location in the cell and stuff like that. So there are many there are other information that we should consider and take advantage of. So here's the slide that summarizes, for me anyways, big data. That gives you the value. So the value is in the integration. And basically, the slide says that you have data in different sources. And this data is completely different from one source to the other. They're collected independently. They may have overlap. They may have contradictions. They may have, they may be in different formats. And so you need to acquire that data. That's not trivial. You need to extract information out of it. So for example, if it's text, if these are tweets, you need to do some natural language processing out of this, extract some named entities, extract some actions. For example, if you have electronic health record, you need to extract the numbers. Is that number blood pressure or posology? So I don't know, how much of this treatment they have to take, or is it a temperature or whatever. So there's information extraction that has to be done. You have data cleaning due to these uncertainties that are in different data sets. You have to represent that data somehow. You have to aggregate some of the numbers. You have to model it, analyze it, and visualize it. So data visualization is extremely important. And finally, it's only at the end that you will be able to interpret something and get something out of it. And for that data interpretation to happen, you need that metadata that follows you from the beginning when the data was created, and it follows the data in its journey until it reaches you, so that you can use it when you are representing the data, when you are extracting the information, when you're doing the analysis itself, and when you're visualizing and trying to interpret. Often we forget the metadata. So when you take these all pieces of the puzzle, then you're able to build this beautiful picture and realize, aha, this is probably in the fall. Again, I'm using metadata because I know that in the fall the leaves fall, and they have different colors. And I may use metadata to say, oh, this is probably in Asia and probably in China, based on the architecture of the roofs and things like that. So this is just to illustrate the importance of metadata. Without that metadata, I may see something, but I may miss a lot of other things. So it's only with that metadata and putting the puzzles together that I will know that what I'm touching is an elephant now. It's not just a tree or a trunk. So here are some examples to illustrate what I'm saying. In 2006, I mean, who knows Netflix, the company Netflix? Okay, not everybody. Netflix is a company that rents movies. Okay, they used to send them by mail, the CD, and now they actually do it online. And they recommend movies to their customers. And that recommendation is based on the rating they gave to previous movies they watched. So they have an algorithm based on something called collaborative filtering that predicts whether you will give a 5-star to this movie or a 1-star to this movie. And then they will recommend the movie where they predict that you would give a 5. So their algorithm is called Cinematch. And it was not accurate 100%. It made errors, of course. But they wanted to improve it, and they couldn't. So they started what they called at that time the Netflix Prize. It's an award of $1 million. Who manages to improve on their error rate by 10%? That's a lot of money. So you can imagine many people started, oh, I can do that. They provided 100 million ratings in a matrix of 500,000 customers and 17,000 movies. They said, here's the matrix that we use. Can you build an algorithm that can improve on our algorithm by 10%? You had la crème de la crème of the machine learning people working on this. And very quickly, they improved. But then they stagnated. and people gave up. This is, I mean, in 2006, you had literally thousands of teams around the world working on this. They had free workers working for them. Many people gave up. They published their solution publicly, say, well, I give up, here's the solution. And the others took that solution, combined it with them, with their own. You had teams that merged and so forth. After 3 years, finally, a team realized, this is how I can do it. They build an ensemble of different solutions together, and they beat that 10%. They got the $1 million. Netflix never implemented that algorithm. Why? First, it was amazingly complex. Second, they realized that, that was a big mistake what they did. They forced people to just focus on that matrix. Had they used all the data, for example, IMDb. Do you know IMDb? It's a public database that has all information about movies, who's the star playing in that movie, who's the director, what's the genre, the year, all that stuff. If you use that information, extra information in your recommender system, you improve not just 10%, you improve way more. So what's the lesson here? Don't just focus on the data that you have at hand. You can access all the data that is publicly available, and you can improve your insights from your own data. So here's another example. Nate Silver. You probably heard of Nate Silver during the elections in the US. So there's a lot of controversy about what he managed to do. So during the elections, you have many companies doing these polling and trying to predict the outcome of the elections. And what he did, he basically took all these poll data and also looked at past data that publicly available from different states. And he created another model that links all this data together. And he published his predictions. And the interesting thing, he was almost right 100% on these elections. Almost 100%. Why? Because he didn't just focus on one data source, but he combined everything together that he could access. And he wrote a book that became a bestseller at that time. Here's another example. This is not to give you names, I just created a hypothetical situation. Imagine this hypothetical telecommunication company. They are selling mobile phone plans, okay? So after a certain time, the plan ends, and you have to decide whether I should keep this customer or let them go, because they churn. They go from one company to the other. Other companies are offering different things for new customers, so they may move. And you ask yourself the question, should I keep them or should I let them go? To keep them, I'll give them some incentives. To let them go, I just ignore whether they renew or not. What is the data you have? You look at the data of your customers. You have typical information, but one column that is important is how much profit you made in the last 3 years on that customer. Okay, so you see some of them are red, okay, even after Black Friday. So they're still in the red, and you're losing money on them. So it seems that they're obviously candidates to remove them. Okay, so here's one strategy you can follow. You can say, I'll sort these are the 19 people that have to renew this month. So I'll sort them by profit, okay? And I say, well, if I did less than $50, here's the top ones, I will just let them go, okay? I didn't make more than $50. If I made more than $50, I'll keep them. Does it seem logical? Yeah. It's the wrong decision. Why is it the wrong decision? Well, I focused on one data set, this table. And I made a strong assumption. The assumption is that these customers are independent. Okay? This is what we call IID data. Independent values are identically distributed in this space. Okay? So in my own company, I have access to other data. What is the other data? I can go and pull and see who's calling who. And here's my new table now. Here I have everybody, okay, who was called or called these 19 people that are renewing their plan. And I can go in my database, not this one, but another database that tells me who called who, and I can build a graph. This graph now, I can even show the frequency of who calls who. I can place now my 6 people, candidate to be removed, I can place them on the graph. And what I notice, and some of them actually seems to be central in that graph. It's not clear yet. If they go, how much money do I lose? Or if they stay, how much money do I lose? It's all based on amount of money. So this is to insist on visualization. Still, it's not clear in that graph. So I'll use another visualization tool. These are concentric circles, where if I'm in the middle, I am more central, where there's centrality measures in graph theory. So I can represent them in that graph. The closer they're in the center, the more central they are, the more on the outskirts that they are peripheral. And then I identify these 6 people. Oh, this guy is peripheral. So if he goes, it's not a big deal. If he goes, not a big deal. Oops, he's coming quite inside. Ooh, there's somebody who's quite central. How much money do I lose if they go? Still not clear. So what I'll do, I'll get that graph, and I'll do what we call in social network analysis community mining. I will cluster it into groups. So here's the clusters that I will get. Again, the importance of visualization. And I color the groups differently. So these groups represent the people who call each other more often than they call on the outside. And then I'll place them again. You can see 2 are in the purple group, 4 are in the yellow group. But still, I don't know how much I would lose. I will represent them again with these concentric circles, and I'll identify, oh, this guy's peripheral. If he goes, not a big deal. Oops, Natalie here, that's Natalie. If she goes, even though I lose on her plan, but if she goes, because she's so central, she may influence people in her community, then the potential risk is $3,000. I'm losing. Let's see the other group. The other group, the yellow group, I have 4 of them. 3 are peripheral. 1 is not that peripheral. He's almost central. So if he goes, he may influence the others as well. And John, in this case, I didn't make a lot of money on John. But if he goes, the risk is $6,000. So now you see, by using other information that I already have in my company, I'm able to make a different decision. Instead of letting go these 6 people, I'll actually give incentives for 2 of them to stay. I'll give them new phones or bonuses or whatever. Okay? So this shows that exploiting additional data and some additional analysis, of course, would allow me to get better insight from my own data and get that competitive advantage. So here's another example. This is an example from Osmar Zaiane. Osmar Zaiane is the first chief data officer in the world. So Yahoo, a few years ago, created that title and named him as the chief data officer because it's the first company that realized this data is an asset, and I want to know, how do I get advantage of my own data that I'm collecting. Today, he's the chief data officer of Barclays, a big bank in the UK, and he mentions how within Yahoo, when he started as a chief data officer, they started looking at their customers, their users, and model them as what they called DNA of a user. So here's my DNA. Okay. And so now many companies do the same thing. So what happens is that as I register as a new customer, I will voluntarily provide some information. For example, here at registration time, I will give my profession, my name, where I live, my address, my phone number, my age, my gender, where I was born, and so forth. That's given to the company. And I know that the company knows that. Okay? That's it. Then what happens, I start buying things. So here's my activity on the site. So for example, I purchased a watch. It's a Garmin swim watch. And I also bought goggles. So whoops, now the company knows that I swim. I didn't tell them that, but they know it. I also browsed, for example, helmets, bike helmets. So they know I have a bicycle, why I'm interested in buying a bicycle. So they may be trying to entice me to buy one. Maybe I do triathlons. Maybe, oh, they're now running shoes and things like that. So they start knowing more things about me. I also purchased an espresso machine. It happens that I purchased it not for myself, but as a gift. I don't drink coffee. But they think I drink coffee. So this is where the uncertainty comes to play. Okay? And they have to deal with it. Okay? So that's for my activity. But there's also my behavior on the site. And they learn a lot from that. For example, I reviewed other products. People are commenting on products, and I reviewed some products. 11 of them, I said something negative about them, and 23, I said something positive about them, the number of stars. They learn from that. I also replied comments on books. Oops, he's interested in books. I searched on home improvement. Oh, he's building a house or something like that, or renovating his house. So they get something out of that behavior. I also suppose on that site I have friends and followers a la Twitter. They can see what also my followers like and purchased and behaved and all that stuff, and my friends, how they purchased. And all that creates my genes, my genome in the company. But it doesn't stop there. Now they can go to web sources. And in web sources, they can do searches on me as a person and find hobbies, habits, my preferences, my work. So they can go to Facebook, find not only what I like, but what my friends like. What my friends like, because they're my friends, it has a lot to say about me. They can go to Twitter, and if it's geolocated, they actually know where I am, where I tweeted about some different topics. They'll go to LinkedIn, know where I worked, where my co-workers worked, and so forth. They can go on Foursquare and know actually my footprints, where I went. They can search different search engines and know a lot more things about me, what I published, about the pictures I published, the pictures I annotated, the annotations, the labels, the hashtags I used, the YouTube I watched, the YouTube I annotated, the YouTubes I posted. Same thing with Wikipedia. What are the articles I followed and changed, I edited. They can go to the news, the blogs, you name it, the forums where I participated, and suddenly they know more about me than I know about myself. And I'm not joking. They can actually predict my emotions. There's sentiment analysis, and we can see when people are happy, when people are unhappy, when there's fear, when there's surprise. All that can be detected, and they know when to approach me with some things and others. Okay. So this is where vulnerability plays a role. That V that I mentioned plays a role, because suddenly by combining all these together, you have something that doesn't exist in any individual data source. Okay, so it's the combination that brings value. Okay, we talked about not big data, big rich data. I prefer using the rich here, because it's really, truly rich. Rich in size, rich in variety, rich in structure, and so forth. Complexity. Now I'd like to talk about some anecdotes where even though we have this power and this potential, today we're still not using it fully. I'll give you some examples. So on one hand, I show you this complex genome of the user or the customer that they're collecting. On the other hand, they still have some issues. So here's some examples. Some of these slides, I also borrowed them from Osama Fayyad. So here's an article in the newspaper on the web page. And when you have an article, there are spots where people can bid on to put their ads. Okay? And then the publisher will select some different algorithms and will put the highest bidder or the second highest bidder or whatever, depending upon the algorithm. So this article talks about body parts. This is a real article. Body parts that were delivered to a private home. These were sent from China to a lab, research lab in the US, but by mistake, they ended up being delivered to a private home, and they open it, and you imagine the shock, and of course the newspaper covered it. What do you think, so you have body parts, what do you think is the ad there? UPS, what else? I think UPS, you're right. UPS. Why? Well, do you think this is damaging to the brand? Definitely. Definitely damaging to the brand. And it has to do with the algorithm that they use. The information is there, but they only focused on one thing. They focused on parts and delivered. But there is what we call opinion mining, where you can see the positive and the negative of some texts. And you can see also the positive and negative vis-a-vis some topics. So exploiting that, well, you wouldn't have bid on that article. Okay. Unfortunately, that is very common. So here's another article. This is, I found it recently. This is actually a few weeks ago. The title says, "Baby found in storm drain, woman charged with attempted murder." This is a real story in Australia, and it was covered internationally. It was a big deal. And I was reading it in Edmonton. And, well, the top advertisement, I hid it. It's irrelevant, luckily. But another one is actually quite interesting. What do you think is in that, I mean, behind that blue label? Suggestions? Not UPS. No, well, it could have been. Yeah, terrible, terrible. No, it's Action Auger something. I hid the name because I don't want to show it. It's in Canada. Again, it's not the right place to put that kind of ad. It's kind of shocking. Here's another example. That's because they used storm drain as just the keyword to identify the thing. They didn't look at opinions. Here's another example. Violence continues in Greece as rioters firebomb buildings. This is during the riot in 2008. As you can guess, here they were advertising for a trip to Greece. It's not the right time. It's not the right time to go to Hong Kong, for example, because they have riots as well, and other places. I've seen, unfortunately, I didn't capture the page when I saw it. You remember when the Malaysian airline disappeared, and I was reading an article about it, and they had an ad about the Malaysian airline itself to go to Kuala Lumpur. It wasn't the right place. Okay, so it's actually feasible by exploiting some of big data capabilities. So here's another example. This is not bad place, but the wrong meaning of the terms. And again, big data, and we have some papers on that, how you can, with more data, you have more accuracy in guessing the different semantics of terms. So here's an article that talks about nail gun. Nail gun is a framework that allows you to run Java not on the virtual machine of the client, but you can run it on the server. So this is a page talking about Java, a nail gun, and the ads are about nail guns. It has nothing to do. Okay, that's all with the anecdotes. I want to talk about the pitfalls, some pitfalls. In 2012, there was an article in the Harvard Business Review saying that a data scientist is the sexiest job that we can have in the 21st century. That was a big deal, and actually it influenced a lot of universities, probably here too, and I think it should. And this was based on a report by the McKinsey company, a McKinsey report in 2011, in which they talked about big data, and they said that by 2018, so very soon, we'll have a shortage of up to 190,000 data scientists in the US alone. Canada will be the same. We won't have enough data scientists. Actually, all the data scientists that we create at U of A, they all go to the States, unfortunately, because they're better paid there. So we will have a problem in Canada as well. More than that, they say that up to 1.5 million managers also would need some training in data analysis and on the know-how of how to do these analysis on big data. So this article led to the article on Harvard Business Review, and that started a big discussion. And what is happening is that because we have a shortage today, you have many people who claim to be data scientists while they don't have the background. They are not real data scientists. So they're data scientists wannabes. So this is a message, since I'm in a university, is a message to universities. We should do an effort to train more data scientists. So there are different kinds of data scientists. There's data scientists that maintain the data, that build the infrastructure, that do the analysis, that present the reports. The data scientists at different levels, and we need them all. The other kind of training we need to do, we ought to do also at the universities, is the training of the managers. Because if the managers are not well trained on data science or the capability, the potential and so forth, they can't leverage the skills of their own engineers. So they need also to do some, we need to do some training. Otherwise, the other effort that we need to do as researchers is something similar to the automobile industry. So maybe we should think about non-data scientists, so creating solutions for non-data scientists. So if you look at the car industry, a century ago, you needed to be an engineer, like for the locomotive. You need to be an engineer to drive that car. You need to know how the carburetor works, how to change the spark plugs, how the drain shaft works, how when the Delco is sending the sparks to different spark plugs and so forth. You need to understand that to fix your car if you're stopped in the middle of nowhere. Today, cars are completely different. You don't care about what's underneath that hood. You don't have to know whether it's a carburetor or an injector, or what's the difference between a carburetor and an injector and so forth. You don't care. Actually, you don't even turn the key anymore. You press a button. You press a button and it works. More than that, for parallel parking, some cars do it for you. So we used to have a key. In the past, we didn't have a key. We had a crank. And actually, you needed power to be able to turn it. Now my grandmother's not here, but old people can drive a car. They don't have to care about how it works. Unfortunately, big data is way in the early stages. So that's the oldest still running car, was built in 1884, I believe. Yeah, in 1884. So we're still there, and we have a long way to go to get that autonomous vehicle where you sit in there and it does it for you. So we need to think about solutions where a non-data scientist can also play with big data and get some insights without having to worry about Hadoop, non-Hadoop, whatever. Okay? The truth is today, this is the situation we're in. We have one hammer called Hadoop, and we try to hammer everything. Everything is a nail. And you get solutions like this. So you use a screw. I didn't have a hammer, so I found a screwdriver. Screwdriver, you can use anything. You can use a screwdriver to solve anything. So the other pitfall has to do with metadata. Unfortunately, we forget it. We ignore metadata. We realize that we need it when it's too late. Metadata needs to be collected at the source when you're getting the data. And the metadata needs to be managed alongside the data, needs to be stored. And if possible, used in the data cleaning and the data analysis and in the interactive, hopefully, visualization that you provide, and finally in the interpretation, so that you can take action on that result. Okay, so metadata should be created at the source, should journey with the data, and managed with the data, and then exploited at the interpretation of the data. Now, the other pitfall is the fact, and I mentioned it before, is the fact that data is pliable. You can make it say whatever you want, especially when you don't have metadata to back it up. So you can make it say what you want it to say. So critical thinking is the killer app for big data. Okay. Results thrown like that in a report are not enough, and we need to work harder on how we visualize these results. I went to a webpage talking about the 15 fantastic examples, and I just put them in here in your website to show you the variety of things we can do in order to represent more than just 2 dimensions in a table. So we need to do that. We, computer scientists and data scientists, we can't do it alone. We have to collaborate with artists and specialists in communications to convey the information in pleasing but useful kind of, hopefully interactive visualizations. Finally, another thing that is an opportunity for research, and it has to do with the speed at which the data is changing. The big problem with the data changing all the time is the fact that not only the data is growing, but the dimensions are being added exponentially as well. And the more dimensions you add, the more complex the data becomes to analyze. And this is also very often forgotten or not even considered, but many algorithms cannot handle a high-dimensional space. And if that high-dimensional space is growing exponentially, forget about those algorithms. Okay, we need to think about new ways of looking at this data. Okay, to summarize a little bit what I was saying, the highlights is, well, this big data phenomenon, again, I don't like big data, the term, but it's not just hype anymore. It's real, it's there. It's going to go down, I predict it, in terms of funding. But it's the believers like you and I in the university and research places and companies that believe in it that will keep it survive, and it'll go up again. So most sectors in the economy are data-driven, and we are collecting this data, and we need to use it to make our better decisions. And this data is not going to stop. It's going to continue to come and become even more complex. More sources will be available. And what we have to do is not just focus on infrastructure or focus just on the algorithms or focus on this or that. It's a holistic kind of solution that we have to think of. Today, most of the effort is on infrastructure. Most of the investments from these companies is in infrastructure to be able to put this data. They are now talking about a data lake. If you Google data lake, you'll see it's going beyond these data warehouses. Unfortunately, these data lakes, we're building them, we're putting everything in there, but we're drowning in these data lakes. We don't know how to do with the data inside. So the challenges are the scale, of course. It's very big, the heterogeneity. It's coming from different data sources, and they may not necessarily use the same kind of terminology. So there's semantic heterogeneity, but there's also other kinds of data heterogeneity. There's contradictions, inconsistencies, and it's only with managing the by using and managing the metadata that we can solve some of these problems. There's the issue of timeliness. It has to be answered quickly, and the issue of privacy. So definitely there are many opportunities for research, for researchers like us at the university. Now I want to ask a quick question, just because I'm here at the university. Who knows about the first MOOC created in the world? You know what a MOOC is? Massive open online courses? You're right. You're right. So in 2008, it was George Siemens and Stephen, what's his name? He's at the NRC now in Moncton. George Siemens now is in Texas, but he created the first large online course, and he created the term MOOC. Today, MOOCs are everywhere. And you have big companies like Udacity, Coursera, EDX, Khan Academy, and so forth. I'm actually honored to be here where MOOCs were created for the first time. The interesting thing is that these MOOCs are generating a lot of data, and this data is not analyzed today yet. I should stop, I can see. Yeah. So unfortunately, these MOOCs are modeled on traditional courses. You have one person and the students around, except that you have many more students. That's it. But you still have one person or a set of instructors providing courses with videos, and there are discussions using forums. So they added these forums. But it's basically not different from e-learning that we did before, except that it's scaled up. And they're using peer evaluation for the assignments and things like that. So MOOC, that I call version 1.0, is just e-learning that is scaled up. However, MOOCs are collecting a lot of data. It's massive. You have hundreds of thousands of people taking each course, and then you have thousands of these courses. Moreover, they're accessing from around the world at different times of the day, and all their activities are coming at you at a high speed. So there is velocity as well. And for variety, man, you have variety. All sorts of information. So not only when they register, you know about all the courses that they took, the grades that they took, but also you have the networking in the system. You know what images they downloaded, what annotations they made, the activities they did in the course, the tests they took, the videos they watched, all sorts of information. You may have done some surveys, whatever. All that information is very rich kind of information. Well, that can be exploited, and this is an invitation, because I'm at the university, I think there's an opportunity here also for research, because if you mine that large, big, rich data, you can improve significantly the life of an instructor using a MOOC. For example, you can automatically identify the learners that have difficulty. You know, the biggest problem with MOOCs is that people drop from the course. So if you can detect it, predict the dropout, before even it happens, then you can highlight those students that need help, and the instructor can help those. Because you have hundreds of thousands, you cannot spot them by yourself. Big data can help you identify those modules or pedagogical units in the course that require improvement. Okay, because now you can see the mass of people, where they make errors and where they are fine. You can understand how the content of the course is used, and so forth. There are many advantages. You can also help the student. You can help the student by particularly adapting and personalizing the course. Like, rather than everybody seeing exactly the same thing, so cookie cutters, you adapt it to the person, to their pace, to their needs, to their background knowledge, their culture, whatever. You can build recommender systems. The list is long. I think I'm going to finish here by trying to link it again to the AI slide that I had before. So big data, I think, is one ingredient important in the recipe of something called the singularity. So what is happening is that our hardware improved significantly since the early days of AI. We have machines. I mean, my cell phone is way more powerful than the computer I used when I was doing my PhD. I mean, it's ridiculous when you think about it. The computer on my watch is more powerful than the onboard computer of Voyager 1 and Voyager 2 that were sent in outer space. It's unthinkable. So these machines are very powerful today. In addition to that, with IPv6, we have now things everywhere that are connected. We call it the Internet of Things. And some of these things have computing power. If we have the right software, and that is what is missing, it's just the software, and we connect them all together, that is what will help us go, or will lead us, I don't know if it's help or it's a bad thing, lead us to what we call the technological singularity. But that is another talk. So here's my last slide, my message to take home. is that there are different perceptions of what data science and big data is, or rich data. There is rich data or big data all around us, and it's capital that we take advantage of that, take a chance to enhance the decision making. We need to educate people and educate new data scientists, but also managers. We shouldn't forget that. Otherwise, our data scientists will not be used properly. Do not forget the metadata. It's a complex data, but if you don't have that metadata, you will not be able to deal with the interpretation of the end properly, at least. You have to be careful that data is pliable. You can make it say whatever you want. So critical thinking, as I said, is the killer app for big data. An invitation for visualization to work with artists and communication people. They have the skills. And we should exploit all obtainable data, not just the data that we have available at hand. So look around. There's public data. There's data that is open. There is data on the web that can enhance what you can get out of your own data. And that's the end of my talk. Thank you.